P over N0 sine lambda L minus A over lambda sine lambda L sine lambda X plus P A minus L over N0L X. For X smaller than A, larger than 0. And P over N0 sine lambda A sine lambda L lambda sine lambda L cosine lambda X minus P over N0 sine lambda A cosine lambda L lambda sine lambda L sine lambda X plus P A N0 LX minus P A N0 for X smaller than L, larger than A. Okay, this is for the spin column, this simple problem. This is a solution, closed form solution. Yeah. Okay, and here lambda is what? Is N0 over EI square root, right? So you can see we have a lot of N0 lambda 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 lambda, okay, lambda N0 lambda 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 lambda, so many lambda N0. Okay, so this equation is nonlinear. Nonlinear with respect to N0, right? But see P, the P here, P here, okay, and the P here, and P here, P here, and P here. So it's linear for P. Okay? So that means we cannot do superposition on N0. Okay? Yeah. You cannot say, okay, I solve this problem with roller, and this is a NY. Okay? And we got a solution. Okay? And the plus N2. The diffraction, and you can get the solution of a P of N1 plus N2, N1 plus N2. These are not equal, okay? So you cannot do superposition on N0 because we have a lot of lambda. It's a nonlinear over N0. Okay, but for P you can use this solution to do some problem for this roller, and we have n0. Okay, and we have like a P1, P2. So I can equal to n0, n0, P1 plus P2. Okay, so this solution will equal to this solution plus this solution. So P is linear. So the diffraction is linear to the loading P. Okay, so if you have a lot of vertical loading for this being under axial compression, the lateral loading can use superposition. See what I mean? So that's why I have to derive this equation for you, solution for you, to see is linear with respect to P. The solution W is linear with respect to W. So we can do superposition. But it's nonlinear with respect to the non-N0, actual loading, compressed loading. So we cannot apply the superposition on N0. Right? So after we got this fundamental concept, then we can do the distributed loading on the beam under actual force, compression force. Okay. Now, let's see the actual displacement. For this N0 compression, okay. So we have a lateral loading, for example. It's my QX, right? After formation, this will be moved to somewhere. So there's some displacement we call delta under actual loading. Here. Yeah. All right. So recall we have the minus N0 equal to sigma x dA. Integral across the cross section will be the actual force, and this will be the Young's modulus times the epsilon x, and this will become AE partial U partial x plus half partial W partial x squared. Okay, remember this equation? Okay. Then from this I can get the partial U partial x, this term, equal to minus N0 over AE plus minus half partial W partial x slope square. Then I integrate both sides. And this will become a du, right? du. Then this du will have a u, 0 and L, and it's equal to the minus N0 over AE times L, dxL, and plus and minus half 0 to L partial W partial X square dx. Okay, this is so that means that the diffraction will cause the movement, and this is a deformation caused by the actual loading. Okay, if do not actual loading for being under diffraction, so theoretically it has this kind of a